Our next topic, back to calculus, but now using it. So, as the name suggests, geometrical application. So what we've looked at so far is basically the first derivative. And so a reminder of the different notations that we can see. There's y dash, f dash x if it's written in function notation, or sometimes we just do d dx of the actual function itself, and probably the most common of them all, simply dy dx. And we found out that when we were doing curve sketching, then dy dx measured the slope of the tangent of the curve. But in general, it just measures a rate of change. Okay. So when it comes to drawing graphs, if we think about this logically, if the derivative is positive, therefore the slope of the tangent is positive. So therefore the actual curve must be going up or rising. Because if you think of drawing a tangent with a positive slope, curve must be going up. And similarly, if it's negative, then we've got a negative slope on the tangent, so the curve must be going down. And the third case is when it's equal to 0. It's not going up, it's not going down, so we call it stationary, and that must be the vertex, I guess, or the turning point of the curve. So our curve, 3x squared minus x cubed, we're going to find all the stationary points, and then we're going to work out what type they are, so determine their nature. Now, the stationary points will usually be either a maximum turning point, a minimum turning point. It is also possible to be a third thing called a horizontal point of inflection. But this particular curve, we won't have to worry about that. And then we're going to go and sketch the curve using that information. So, all right, we're going to need our derivative to find the stationary points. Remember, the setting out of this question is important. You're explaining to people what you're doing. Because if they're reading your solution, they need to be able to interpret it. So once I've found my derivative, I would make the statement, well, okay, I know the stationary points are going to occur when the derivative is equal to 0. And that explains why we're making the derivative equal to 0. I'm trying to find stationary points. And this is a nice simple quadratic because it factorises. So we've got x equals 0 or x equals 2. Need to find the y values, of course, to complete the question because it did say find the actual point. So 0, 0 turns out to be one coordinate, and the other one, when we substitute back into the y value, we get 2, 4. Okay, let's have a look at 0, 0. Now, if I investigate around the stationary point, I'll be able to tell what the curve's doing. So what we do is, obviously in my table of values, the middle one will be the stationary point that I found. So I know it's stationary. I'll just draw a horizontal line because it would be a horizontal tangent at that point. I need to pick a point on the left-hand side of 0 and the right-hand side of 0 so I can see what the curve's doing before and after the stationary point. The only rule when you're choosing these points is do not go past either another stationary point or any points of discontinuity. So on the left-hand side, I'm right because there's nothing on the left-hand side. So I could pick any point, and I've just put a negative there to say on the negative side, I could pick anyone. And so then on the positive side, I won't go past 2. So on the negative, I've chosen negative 1. That's a pretty easy one to sub in. And when I sub in negative 1, I get negative 9. So I know the curve's going down at that point. Okay, on the right-hand side, we don't go past 2. So again, I'll pick 1. That's a nice easy one. And that turns out to be positive 3. So I've got a bit of a picture. By drawing the picture of the tangents in there, it gives me a bit of a visual idea of what's happening. Curve's going down, stationary, then going up. So we have a minimum turning point. Then 2, 4. Again, let's draw up our table of values. So in the middle we have 2, which we know is our stationary point. I'll have a horizontal there. I'll pick a point on the left-hand side or the negative side of 2 and one on the positive side. Now, I'm going to pick 1 because I've already worked it out. Not only is it on the right-hand side of 0, it's also on the left-hand side of 2. So why give myself any extra work? And we've already worked out that's positive 3. And on the right-hand side, there we go, sub in 3. And a bit of a coincidence, turns out to be negative 9. So this one's going up, stationary, going down. So I know it's a maximum turning point. All right, let's draw it. There's 0, 0. and up there is 2, 4. Now the diagram itself, because I know this is continuous, I should realise that 0, 0 is going to be the minimum, and 2, 4 is going to be the maximum. Yeah. So there's 0, 0. Now, if I had just done my working out, and I found 2, 4 to be a minimum, or 0, 0 to be a maximum, use your common sense, right? And use the information to go, hang on a sec, something's wrong here, because that just doesn't tally up with what I've just plotted. Go back and check your working out, see which one's wrong. But we got it right. So we know that's a minimum, that one's a maximum, so I must have something that does that. It's a very basic sketch, this one. I haven't bothered to find out the other x-intercept, although would it be easy to find for this curve? What was our equation? So we could. With x-intercepts, I usually only find them if they are simple to find. Although, as it turns out, this one was easy to find. I could have done that. And the y-intercept's always easy to find, but we've already got it anyway. It's 0, 0. As we develop our calculus further and further, we'll be able to find more points more accurately and things like that. But at this stage, just using the first derivative, it's probably good enough to get a shape of the curve. We've got a feel for what the curve is doing. Okay, 10A, 10B, bit of revision on our first derivative, a reminder of what we did back a term ago, and 10B as well.